In the crisp autumn of 1943, a Republic P-47 Thunderbolt, an iconic American fighter, lay abandoned in a French field, a testament to a pilot's narrow escape during a perilous low-level strafing mission. While its propeller was twisted and its landing gear buckled, the aircraft remained remarkably intact, a prime target for German acquisition. This formidable 7-ton marvel of American engineering quickly became the property of the Luftwaffe. Within mere hours, German recovery teams descended upon the crash site with the fervor of archaeologists unearthing an extraordinary, perhaps even extraterrestrial, artifact. They were certainly no strangers to downed Allied aircraft, having encountered numerous Spitfires, P-38 Lightnings, and even the occasional B-17 Flying Fortress. However, the Thunderbolt presented a unique enigma. Its sheer bulk was astonishing, almost grotesquely heavy for a single-engine fighter, and its formidable reputation among Luftwaffe pilots had already blossomed into something bordering on legend. The meticulous recovery operation was a delicate endeavor, executed with surgical precision. German mechanics carefully disassembled the aircraft, systematically loading its primary components onto sturdy flatbed trucks. This precious cargo was then transported to Rechlin, the Luftwaffe's principal testing facility, strategically located approximately 60 miles north of Berlin. Rechlin was far more than a mere airfield. It served as the veritable nerve center of German aviation intelligence, where captured enemy aircraft underwent an exhaustive and rigorous analysis. By late 1943, the facility had transformed into an eclectic, almost surreal museum of Allied air power, a place where American, British, and Soviet aircraft stood in stark juxtaposition with advanced German prototypes, creating a vivid tableau of the competing philosophies that defined the air war. The arrival of the P-47 at Rechlin ignited an immediate spark of excitement among the technical staff and seasoned test pilots. For months, they had been receiving troubling dispatches from the Western Front. Luftwaffe pilots consistently reported that American fighters, particularly these resilient Thunderbolts, possessed an uncanny ability to absorb battle damage that would undoubtedly obliterate a Messerschmitt Bf 109 or a Focke-Wulf FW 190. Pilots recounted expending entire ammunition loads into P-47s during intense aerial engagements, witnessing their cannon shells strike home with undeniable impact, only to observe the American fighter continue its trajectory as if utterly unfazed. Some pilots began to suspect their ammunition was defective, while others pondered whether American metallurgical advancements had somehow surpassed German capabilities. The more superstitious among them whispered about the Americans having developed some form of impenetrable force field technology. German intelligence officers desperately needed definitive answers. The Eastern Front was relentlessly consuming resources at an astronomical pace, and the Luftwaffe simply could not afford to squander precious ammunition on aircraft that appeared impervious to it. If the P-47 truly harbored some revolutionary defensive technology, Germany had an urgent imperative to comprehend it, replicate it, or devise effective countermeasures. The captured Thunderbolt thus represented an unparalleled opportunity to unravel this profound mystery through direct, hands-on examination, rather than relying on mere battlefield conjecture. Stay with us and watch the end of the video. We will be grateful for your like and subscription. The exceptional value of this particular aircraft was further magnified by its remarkably intact condition. Unlike the majority of captured planes, which typically arrived as twisted, irreparable wreckage necessitating extensive and costly reconstruction, this P-47 required only relatively minor repairs to be rendered airworthy once more. Its powerful engine remained fully intact, the airframe exhibited no significant structural damage, and most of its intricate internal systems appeared to be fully functional. German mechanics confidently estimated that they could have it soaring through the skies within a matter of weeks. More crucially, this pristine condition allowed them to subject the aircraft to the kind of destructive testing that would unequivocally reveal precisely why these formidable aircraft continued to survive combat damage that, by all conventional standards, should have proven fatal. The stage was meticulously set for one of the most profoundly revealing aircraft evaluations of the entire war. The P-47 Thunderbolt was undeniably not conceived with aesthetic beauty as its primary objective, nor was it ever intended to be a lightweight fighter. When Republic Aviation's brilliant design team convened in 1940 to engineer a fighter around the colossal Pratt & Whitney R2800 double wasp engine, they made a pivotal and conscious decision that would intrinsically define every aspect of the aircraft's character. Paramount survivability would unequivocally triumph over elegant design. The R2800 was an absolute behemoth, an 18-cylinder radial engine capable of generating a staggering 2,000 horsepower, a figure later boosted to over 2,500 horsepower in subsequent variants. To provide a clear perspective, the formidable Bf-109G produced approximately 1,475 horsepower, and even the potent FW-190A peaked at around 1,700 horsepower. The Thunderbolt possessed a raw, unadulterated power that contemporary German fighters simply could not rival. However, such immense power came with inherent consequences. The P-47D, the most prevalent variant, tipped the scales at approximately 10,000 pounds when empty, and could reach an astounding 17,500 pounds when fully loaded with fuel, ammunition, and ordnance. This made it roughly twice as heavy as a standard Bf-109. German engineers, meticulously examining the captured aircraft, could scarcely believe that a single-engine fighter could attain such prodigious weight and still operate with such remarkable effectiveness. Their own design philosophy vehemently emphasized lightweight construction and exceptional agility, prioritizing the ability to outturn an opponent in the close-quarters ballet of a dogfight. The Americans, it appeared, had adopted the diametrically opposite approach, constructing what was essentially a flying tank, a behemoth of aerial warfare. The colossal dimensions of the Thunderbolt stemmed, in part, from its sophisticated turbocharger system. In stark contrast to German fighters, which utilized mechanically driven superchargers mounted directly onto their engines, the P-47 employed a massive General Electric turbocharger ingeniously positioned in the rear fuselage. Superheated exhaust gases from the engine dynamically spun a turbine, which in turn drove a compressor, effectively forcing air into the engine at high altitudes, where the thin atmosphere would otherwise starve it of vital oxygen. This intricate system necessitated extensive ducting that traversed the entire length of the fuselage, channeling scorching exhaust gases rearward and compressed air forward. The engineering was undeniably complex, inherently heavy, and somewhat prone to leaks, yet it bestowed upon the Thunderbolt phenomenal high-altitude performance. At an altitude of 30,000 feet, where Bf-109s and FW-190s struggled for air and experienced significant power loss, the P-47 continued to produce its maximum horsepower with unwavering efficiency. The fuselage itself was constructed with the formidable resilience of a fortress. Republic's astute engineers had meticulously studied combat damage reports from early war fighters and concluded that the vast majority of fatal hits occurred in predictable and vulnerable locations: the engine, the cockpit, and the fuel system. Consequently, they armored virtually everything. The pilot was ensconced behind a robust 1/4-inch steel plate on his seat back and protected by thick bulletproof glass directly in front of him. Additional armor safeguarded the powerful engine from frontal assaults. The fuel tanks incorporated a revolutionary self-sealing design, featuring multiple layers of rubber that would ingeniously swell and effectively close bullet holes upon exposure to fuel. While similar technology existed in British aircraft, the Americans had refined it to an exceptional degree of effectiveness. Furthermore, there was an astonishing degree of redundancy meticulously built into every critical system. The P-47 boasted multiple fuel pumps, comprehensive backup electrical systems, and control cables strategically routed through various distinct parts of the airframe, ensuring that a single cannon hit could not simultaneously sever them all. The sophisticated cooling system for that enormous engine was intelligently distributed across a large area, meaning that localized damage would not precipitate immediate and catastrophic overheating. German fighters, meticulously engineered for minimum weight and maximum performance, possessed no such redundancy. A single 20mm shell, precisely placed, could irrevocably destroy a Bf-109's cooling system, compelling the pilot to shut down the engine within minutes, or face the grave risk of catastrophic failure. The German technicians at Rechlin possessed a fundamental understanding of the P-47's basic specifications even before they commenced their comprehensive evaluation. However, comprehending numbers on paper and experiencing the formidable aircraft firsthand were two entirely distinct propositions. Rechlin was not simply assigning random pilots to captured aircraft. The Luftwaffe maintained a highly specialized unit known as Circus Rosarius, named after its esteemed commander, Theodore Rosarius, specifically tasked with the critical mission of evaluating enemy equipment. By 1943, this unit had evolved into one of the most elite groups within the Luftwaffe, staffed by seasoned combat veterans, who possessed not only the skill to fly but also the profound ability to analyze an aircraft's inherent strengths and weaknesses from a crucial operational perspective. These were not test pilots in the peacetime sense. They were hardened warriors, who had survived hundreds of arduous combat missions, and could instantaneously recognize whether a particular design feature would truly matter in the crucible of actual battle. Hermann Graf was among the distinguished aces specifically selected for the P-47 evaluation. By late 1943, Graf had accumulated an astonishing record of over 200 confirmed kills on the Eastern Front, solidifying his reputation as one of Germany's most successful fighter pilots. He had piloted everything from the early Bf-109E models to the very latest FW-190A8s, endowing him with an encyclopedic understanding of fighter aircraft handling characteristics. The Luftwaffe specifically sought pilots of Graf's caliber because they would not be swayed by novelty or intimidated by foreign technology. They would evaluate the Thunderbolt with the same cold, methodical precision they applied to assessing a potential opponent in combat, dispassionately, systematically, and relentlessly searching for any vulnerabilities to exploit. Alongside Graf, several other highly experienced pilots rotated through Rechlin for the rigorous evaluation. Hans Werner Lurk, another decorated pilot, dedicated considerable time to scrutinizing captured Allied aircraft, and would later extensively document his invaluable experiences. These men fully understood that their meticulous reports could profoundly influence Luftwaffe tactics across the entire Western Front. If they discovered that the P-47 possessed a critical weakness, perhaps an inability to turn tightly at low speed, or perhaps significant blind spots in the cockpit, that vital information would be rapidly disseminated to fighter squadrons within days. Conversely, if their evaluations confirmed that the Thunderbolt was indeed as tough and resilient as frontline pilots claimed, the Luftwaffe would be compelled to adjust its entire strategic approach to engaging American fighter escorts. I am from the United States, and I find this video topic absolutely fascinating. It offers a rare glimpse into the meticulous intelligence gathering and operational analysis conducted during wartime. the German perspective on the P-47's sheer durability, and the methodical approach to understanding its strengths and weaknesses is incredibly insightful. It really highlights the ingenuity and contrasting design philosophies of the Allied and Axis powers. The rigorous evaluation process at the Rechlin testing facility adhered to a meticulous procedural framework. Initially, test pilots commenced with comprehensive walk-around inspections, carefully scrutinizing the aircraft's fundamental construction, its integrated armament systems, and various operational components. Their detailed assessment extended to an exhaustive study of the cockpit's ergonomic layout, specifically noting the precise placement of critical controls by American designers and critically comparing the panoramic visibility offered to that of indigenous German fighter aircraft. Following this internal and external appraisal, ground engine runs were conducted to ascertain the power plant's unique operational characteristics. Only after this exhaustive preliminary assessment did the team venture into actual flight testing, which itself progressed through a carefully modulated sequence, beginning with brief, low-altitude hops around the airfield, then gradually escalating to advanced aerobatic maneuvers, high-speed dives, and intricate simulated combat scenarios. Every facet of this extensive operation was obsessively documented. German technicians meticulously photographed every minute detail, took precise measurements, and compiled exhaustive technical reports destined for distribution to various aircraft manufacturers and the highest echelons of Luftwaffe command. Their objective transcended a mere understanding of one captured P-47. They sought to dissect the entire American design philosophy. Pertinent questions arose. What valuable lessons could German engineers extract from this formidable aircraft? Were there innovative features worthy of replication? Conversely, were there inherent flaws that could be strategically exploited in aerial engagements? Furthermore, these evaluations incorporated an element of psychological warfare. The Luftwaffe, on occasion, deployed captured Allied aircraft in combat, repainting them with distinctive German markings and flying them against Allied formations to sow confusion and hesitation. A P-47 emblazoned with Luftwaffe insignia, appearing unexpectedly in a critical sector, could induce momentary indecision among American pilots, a fleeting pause that in the crucible of aerial combat often proved irrevocably fatal. However, such a tactic was only viable if German pilots possessed a profound and nuanced understanding of how to operate the appropriated aircraft convincingly enough to pass for Allied aviators, at least from a distance. As the Rechlin team braced themselves for their inaugural flights in the formidable Thunderbolt, they carried with them the cumulative wisdom gleaned from hundreds of air battles and an intense, burning curiosity regarding whether this colossal American fighter could genuinely fulfill its rapidly burgeoning reputation. Upon settling into the P-47's cockpit, Hermann Graf immediately grasped the physiological requirement for American pilots to possess a certain height. The cockpit, while not exhibiting the claustrophobic confines of some German designs, actually offered a greater internal volume than a Messerschmitt Bf 109. However, its entire layout was unmistakably tailored for an aviator with longer limbs than the average German airman. The rudder pedals were positioned considerably forward. The control stick emerged from the floor at an unaccustomed angle, and the instrument panels seemed to recede into the distance. Where German fighters enveloped their pilots like a bespoke suit, the Thunderbolt conveyed the sensation of occupying a small, functional room. The visibility, conversely, proved nothing short of revelatory. The P-47's distinctive bubble canopy, a feature introduced with the D model, afforded an almost uninterrupted 360-degree vista, rendering the Bf 109's heavily framed canopy akin to peering through a narrow letterbox aperture. Graf found he could effortlessly glance directly behind himself without physical strain, scan the airspace above and below with minimal head movement, and maintain an unobstructed view of both wingtips. In the context of aerial combat, this would confer an enormous, decisive advantage. Luftwaffe pilots had painfully learned that the majority of successful kills originated from attacks the victim never perceived. The P-47's superior canopy design unequivocally made surprise attacks significantly more arduous to execute. Initially, the instrument layout presented a bewildering puzzle to the German pilots. American designers had adopted an entirely different organizational logic. Airspeed was measured in miles per hour rather than kilometers, altitude in feet instead of meters, and a perplexing array of gauges monitored systems that simply did not exist in typical German fighter aircraft. There were, for instance, multiple selectors for fuel tanks, reflecting the P-47's distributed fuel storage in its fuselage, wings, and even external drop tanks. A complex turbocharger control system incorporated various regulators and pressure gauges. The electrical panel alone boasted more switches than the entirety of a Bf-109E cockpit. It required Graf and his fellow pilots several arduous hours merely to comprehend the function of each control, and an even longer period to commit the intricate engine startup sequence to memory. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. The armament switch panel unequivocally unveiled another cornerstone of American design philosophy, the doctrine of overwhelming firepower. The P-47D was equipped with 8 formidable Browning M2.50 caliber machine guns, precisely 4 mounted in each wing, each supplied with approximately 425 rounds of ammunition. This configuration translated to an astonishing total of approximately 3,400 rounds available for deployment. In stark contrast, a typical Focke-Wulf FW-190AA generally carried 4 20mm cannons and 2 13mm machine guns, but with a considerably smaller overall ammunition capacity. The American strategy clearly emphasized a sheer volume of fire, engineered to project a cone of bullets so intensely dense that effective evasion became an almost insurmountable challenge. The German methodology, conversely, prioritized concentrated hitting power, fewer individual shots, yet each projectile possessed the potential for catastrophic, decisive damage. Neither philosophical approach was inherently superior. Rather, they merely reflected divergent tactical doctrines and operational priorities. What struck Graf most profoundly was the aircraft's exceptional level of comfort. The pilot's seat was generously padded, the cockpit environment was heated with remarkable efficiency, and there was even the thoughtful inclusion of a relief tube for extended missions, a seemingly minor amenity that assumed immense significance during arduous 4-hour escort sorties to Berlin and back. German fighter aircraft, by design, were optimized for brief, intense interception engagements, rarely remaining airborne for more than 90 minutes. The P-47, conversely, was unequivocally conceived for marathon missions, with ergonomic considerations that prioritized pilot endurance and sustained operational efficiency over the absolute minimum weight. The control stick incorporated electric trim switches directly into its grip, enabling the pilot to precisely adjust the aircraft's balance without needing to disengage a hand to reach for separate trim wheels. This might appear a trivial detail, yet in the maelstrom of aerial combat, maintaining continuous contact with both the throttle and the stick could literally delineate the boundary between survival and demise. The oxygen system represented another significant revelation. It utilized a sophisticated demand regulator that automatically modulated oxygen flow based on the prevailing altitude, a stark contrast to German systems, which necessitated manual adjustment by the pilot. Again, this was a seemingly small detail, but one that substantially diminished pilot workload during the chaotic intensity of high-altitude combat. The American engineers had demonstrably considered every conceivable aspect of the pilot's operational experience, striving to make the aircraft as intuitively easy to fly as possible, thereby allowing the pilot to concentrate fully on the exigencies of fighting rather than the complexities of system management. Graf had not even initiated engine startup, and already the Thunderbolt was fundamentally challenging his deeply ingrained assumptions about fighter aircraft design. The powerful R-2800 double Wasp engine roared to life, with a deep, resonant bellow that was distinctly different from the characteristic high-pitched scream of a Daimler-Benz inline engine. Graf meticulously allowed it to warm up in strict adherence to the checklist that mechanics had painstakingly translated from captured American operational manuals, carefully monitoring the cylinder head temperature gauges as they steadily climbed into their designated green arcs. The entire aircraft vibrated with a palpable sense of barely contained power, and he had not even advanced the throttle from idle. When he finally disengaged the brakes and began to taxi toward the runway, the P-47's immense weight became immediately and strikingly apparent. It did not traverse the ground with the agile, almost delicate dance of a Bf-109. Instead, it moved with a deliberate, lumbering gait, necessitating heavy applications of the brakes to control its speed and aggressive bursts of throttle to initiate movement from a complete standstill. The takeoff roll proved considerably longer than Graf had anticipated, even with the prodigious power of that massive engine. The Thunderbolt accelerated steadily, but not explosively, its substantial mass demanding a greater length of runway than any single-engine fighter he had previously flown. At approximately 100 miles per hour, he gently eased back on the control stick, and the P-47 lifted off smoothly, ascending from Rechlin with a remarkable stability that felt almost akin to piloting a bomber. The ailerons, in particular, demanded genuine physical muscle to manipulate effectively at high speeds, and the elevator felt as though it was moving through molasses when contrasted with the light, sensitive touch required in a Bf-109. Yet, within that heaviness resided an exceptional degree of precision. When Graf commanded a turn, the P-47 responded with the exact magnitude he desired, then seized its maneuver without any hint of overcorrection or unwanted bobbling. It was stable to the point of feeling almost reluctant to engage in rapid maneuvering, but that very stability would prove immeasurably valuable as a steadfast gun platform. German pilots frequently struggled to maintain their aim during high-speed attacks because their fighters were inherently so sensitive and responsive. The Thunderbolt's heavy, deliberate controls would ensure the gun sight remained rock-steady on target. Then Graf pushed the nose down and fully opened the throttle. This was the moment to ascertain the veracity of the Thunderbolt's formidable reputation, and the German pilots needed to understand if the widespread stories were true. The airspeed indicator climbed with alarming rapidity. 300 miles per hour, 350, 400, 450. Throughout this acceleration, the aircraft remained absolutely rock solid. There was no buffeting, no disconcerting tendency to tuck or pull itself into an even steeper dive. Even at 500 miles per hour, speeds that would typically induce control surface flutter and structural integrity concerns in most German fighters, the P-47 still felt remarkably controllable. Graf pulled back on the stick to recover, and the Thunderbolt effortlessly converted its immense dive speed into a powerful, soaring climb that propelled him back up several thousand feet in a matter of seconds. This was the Thunderbolt's undeniable killer advantage. In combat, A high-speed diving attack immediately followed by a steep zoom climb represented the safest and most profoundly effective fighter tactic. The attacking pilot dove upon his target with enormous velocity, unleashed a quick, devastating burst of fire, then utilized that accumulated speed to rapidly climb back to a position of safety and altitude before any retaliation could be effectively mounted. The P-47 possessed the capability to dive faster than any aircraft flown by the Luftwaffe, and crucially, could sustain those blistering speeds for considerably longer durations. A Bf-109 pilot attempting to pursue a diving Thunderbolt would be faced with an enviable choice: either break off the pursuit entirely, or risk exceeding his own aircraft's structural limits with potentially catastrophic consequences. And if, by some improbable chance, a German pilot did manage to catch a P-47, the American aviator could simply advance the throttle to its maximum setting and extend away, utilizing the Thunderbolt's superior speed to decisively break contact. The evaluation of the captured P-47 Thunderbolt revealed a complex picture of its aerial capabilities. When put through its paces and turning maneuvers, the aircraft demonstrated clear limitations. Graf, an experienced pilot, noted that during a hard turn at medium altitude, the P-47 exhibited a wide turning radius and rapidly diminished its kinetic energy. This characteristic suggested that formidable German adversaries, like the Bf-109 or Fw-190, could readily outmaneuver the Thunderbolt in a sustained circling engagement, thereby gaining a tactical advantage for firing. However, Graf's astute observation led him to a crucial insight. American pilots, understanding these inherent characteristics, likely avoided such close-quarters dogfights. Their tactics would instead leverage the P-47's superior attributes, its formidable speed, excellent high-altitude performance, and impressive zoom climb capabilities. These strengths allowed Thunderbolt pilots to dictate the terms of engagement, choosing precisely when to initiate combat and when to disengage, thus compelling German pilots to fight on conditions advantageous to the Americans. Over several days, various pilots continued these evaluation flights, meticulously exploring the Thunderbolt's performance envelope. A consensus quickly emerged. The P-47 was not a traditional dogfighter in the European mold, but it was an exceptionally potent combat aircraft when its inherent strengths were fully exploited. While these flight tests thoroughly addressed questions about the aircraft's performance, they left one profound enigma unresolved. How did these P-47s manage to survive damage that, by all conventional understanding, should have proven catastrophic? Luftwaffe pilots were not merely imagining things. Combat footage from gun cameras unequivocally depicted 20mm cannon shells striking P-47s directly, creating unmistakable explosions upon impact. Yet these American fighters remarkably continued their flight. German intelligence urgently sought to determine whether this extraordinary resilience was attributable to sheer luck, superior construction methodologies, or some specific design feature that could potentially be countered. This urgency was amplified by reports of aircraft returning to base with numerous perforations, extensively shredded control surfaces, and damaged engines, only to be repaired and flown again the very next day. In response, the Rechlin team opted for a direct and decisive approach. They would subject the captured P-47 to live fire from their own armaments to precisely ascertain the nature and extent of the damage incurred. This methodology was not entirely without precedent. The Luftwaffe had previously conducted weapons effectiveness tests on captured aircraft, typically by mounting the target on a static stand and firing at it from various angles to simulate actual combat scenarios. However, the P-47 test was designed to be far more comprehensive. The plan involved targeting critical systems, including the engine, fuel tanks, control surfaces, and the cockpit area, and meticulously documenting the maximum damage the aircraft could withstand before becoming irrevocably unflyable. The primary weapon designated for this rigorous testing was the MG-151-20, the ubiquitous 20mm cannon that had become standard armament in most Luftwaffe fighters by 1943. This formidable weapon propelled a 115-gram high-explosive incendiary shell at an approximate muzzle velocity of 720 meters per second. In actual combat, a single, accurately placed hit from an MG-151-20 possessed the destructive potential to obliterate vital components, sever critical control cables, or ignite fuel tanks. Most German pilots generally believed that 3 to 5 solid hits were sufficient to bring down any Allied fighter. For instance, the FW-190A8 typically mounted 4 of these cannons, endowing it with devastating firepower, albeit with a limited ammunition supply, roughly 250 rounds distributed across all 4 weapons, which equated to approximately 5 seconds of sustained firing. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Please write a comment about where you are from and what you think about the video topic. The meticulous test setup demanded careful and precise planning. German engineers positioned the P-47 on the Rechlin firing range, securing it firmly to prevent any movement, while ensuring that all its systems remained fully accessible for subsequent post-test inspection. To simulate realistic combat conditions and rigorously test the efficacy of its self-sealing technology, the fuel tanks were filled with actual aviation fuel. The cockpit, a critical area, was instrumented with an array of pressure sensors and cameras designed to document precisely what occurred when rounds penetrated the pilot's vicinity. Furthermore, a dummy was strategically installed in the pilot's seat, positioned directly behind the armor plate, to ascertain the true protective capabilities of the aircraft's defensive systems. Several MG-151-20 cannons were strategically mounted at various positions around the aircraft, meticulously chosen to replicate diverse attack angles encountered in real combat. In actual aerial engagements, fighter aircraft seldom attack from perfectly perpendicular trajectories. The majority of attacks originated from the rear quarter, slightly above or below, as the aggressor sought to close into firing range while simultaneously evading defensive fire. The test was meticulously designed to replicate these realistic angles, with shots directed at the engine from a shallow angle mimicking a typical pursuit attack, impacts on the wings from the side to assess fuel tank vulnerability, and strikes on the tail section to observe the control system's response to damage. The selection of ammunition was equally crucial. German 20mm rounds were available in several distinct varieties: armor-piercing rounds for engaging bombers, high-explosive incendiary rounds specifically for fighters, and mixed belts that alternated between these types. The test would utilize combat-loaded ammunition, precisely the same mix carried by Luftwaffe pilots on actual missions. This included the potent meningescus rounds, thin-walled shells packed with a greater quantity of explosive than typical cannon ammunition. These rounds were known for their devastating effectiveness against aircraft, capable of inflicting massive damage with a single, well-placed hit. Observers from various Luftwaffe technical branches converged to witness this pivotal event. This endeavor was not merely about satisfying academic curiosity. If the P-47 proved vulnerable to specific attack methodologies, that critical information would be immediately actionable. Conversely, if it demonstrated significant resistance, the Luftwaffe might need to develop new ammunition types or refine existing tactics. There was also a significant underlying concern regarding resource allocation. Germany was already under immense strain to produce sufficient aircraft and ammunition for multiple fronts. If current weapons proved ineffective against American heavy fighters, the Reich could ill afford to continue squandering precious ammunition on attacks that failed to yield decisive results. The test crew meticulously loaded the cannons, verified the functionality of all measuring equipment, and prepared to definitively answer whether the P-47 Thunderbolt was truly as indestructible as its reputation suggested. The first cannon discharged with a sharp, resonant crack that reverberated across the Rechlin test range, propelling a 20mm shell directly into the P-47's engine cowling. The impact was instantaneous, marked by a vivid flash of orange as the high-explosive round detonated, immediately followed by the appearance of a visible hole punched through the metal. The observers meticulously documented the results and prepared for the subsequent shot. This was not conceived as a single-bullet examination. The intention was to subject the Thunderbolt to the kind of sustained firepower it might realistically encounter during an actual combat engagement, emptying multiple cannon magazines into critical areas to simulate a determined assault by an experienced pilot. More rounds relentlessly slammed into the engine section from various angles. Each impact created a distinct and observable pattern of damage. Some rounds cleanly perforated the structure, leaving clear entry and exit holes, while others detonated internally within components, generating fragmentation damage that radiated outwards from the point of impact. The colossal R-2800 engine absorbed hit after punishing hit. Cylinders fractured, cooling fins shattered, and substantial chunks of the cylinder head broke away. The accessory section, where vital components such as generators and hydraulic pumps were mounted to the engine, sustained several direct impacts. By any conventional assessment, this engine should have been utterly destroyed, rendered completely inoperable, a total and irrecoverable loss. The German gunners then shifted their precise aim to the wings, specifically targeting the fuel tanks. This was the point where catastrophic failure was anticipated. Aviation fuel is inherently volatile, and 20mm high-explosive incendiary rounds were expressly engineered to ignite fuel tanks. A single, accurate hit on an unprotected tank was expected to transform an aircraft into a blazing inferno. The Luftwaffe had witnessed countless Allied aircraft erupting in midair after a fortunate cannon hit found a fuel tank. The P-47 carried multiple tanks distributed within its wings and fuselage, boasting a total capacity exceeding 300 gallons. One well-placed hit was expected to convert this aircraft into a raging bonfire. The first 20mm round struck the left-wing tank with pinpoint accuracy, dead center. The observers braced themselves for an explosion or, at the very least, visible flames. Instead, they observed fuel spraying from the entry and exit holes, creating a brief, ethereal mist in the air, and then nothing. There was no fire, no explosion. The fuel simply leaked out and formed a pool on the ground beneath the wing. The gunners fired again and again, punching multiple holes through the wing tanks from various angles. Each time, fuel leaked out, but not once was there any ignition. The self-sealing technology was unequivocally effective, but even more remarkably, the high-explosive rounds were failing to create the necessary fuel-air mixture required for combustion. The tanks were evidently engineered with sufficient internal structure that even explosive cannon shells could not inflict the catastrophic damage needed to ignite the fuel. Attention subsequently shifted to the cockpit area. German fighters typically featured minimal armor protection, and a 20mm hit anywhere near the pilot's position was almost invariably fatal. The P-47's armor plate, situated behind the pilot's seat, was designed primarily to intercept rifle-caliber rounds and shell fragments. However, could it withstand a direct hit from a 20mm cannon? The answer was a definitive no. A direct hit on the armor plate would indeed penetrate. Yet, the test revealed a more intriguing aspect. The armor was positioned and angled in such a way that a direct, perpendicular hit was rendered extremely improbable. Most rounds struck at oblique angles, and even when they achieved penetration, the armor effectively deflected them sufficiently to ensure that the dummy in the pilot's seat remained relatively protected. The tail section was subjected to brutal and relentless attention next. Control cables, hydraulic lines, and the structural components that secured the tail surfaces to the fuselage all sustained direct impacts. The rudder was extensively shredded. The elevator was perforated with multiple holes. And the vertical stabilizer bore a resemblance to something that had been attacked with a colossal cheese grater. This magnitude of damage would typically render most aircraft completely unflyable. Control surfaces necessitate a smooth and intact profile to function correctly. Any significant damage would inevitably compromise the pilot's ability to control the aircraft, particularly at high speeds where aerodynamic forces intensely amplify every imperfection. After approximately 50 20mm projectiles had been discharged into various sections of the aircraft, the gunnery personnel ceased their offensive. A haze of smoke permeated the test range, emanating from spent propellant and several smoldering components, yet there had been no cataclysmic detonation, no immense inferno, nothing that evinced the characteristics of a definitive combat kill. The P-47 remained there, visibly battered and riddled with perforations, but its fundamental structure endured. The true assessment, however, would unfold during the subsequent post-firing inspection, when expert engineers could meticulously scrutinize precisely what elements had withstood the onslaught and which had succumbed. The dedicated inspection contingent approached the heavily perforated P-47, armed with clipboards, cameras, and a profound sense of professional astonishment. From a considerable distance, the aircraft presented an appearance suggesting it could never again attain flight. Upon closer examination, the extent of the damage proved even more comprehensive than initial observations had indicated. The engine cowling appeared utterly perforated, akin to a colander, with jagged apertures revealing the intricate cylinder banks nestled beneath. The wings displayed conspicuous injury, some of the resulting breaches being sufficiently vast to admit a human fist. The fabric covering of the tail section hung in shredded fragments, where it had not been entirely obliterated by the impact. Yet, as the engineers embarked upon their methodical examination, they consistently encountered the same perplexing truth. Critical operational mechanisms sustained injury, yet avoided outright obliteration. The engine inspection yielded the first major revelation. Indeed, multiple cylinders had been struck. Affirmative, cooling fins were fractured and various accessory components lay shattered, but the massive, robust crankcase itself, the colossal and inherently resilient central housing that formed the very core of the R-2800, remained remarkably intact. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. German engineers swiftly recognized that the sheer volumetric scale of the radial engine provided an intrinsic safeguarding capability. With 18 cylinders meticulously arranged in 2 distinct rows, the loss of merely 2 or 3 cylinders still left a formidable 15 functioning. The engine might operate with a noticeable tremor, it might experience a significant diminution in power output, but crucially, it would continue to operate. A liquid-cooled inline engine, such as the DB605 found in a BF109, lacked comparable fallback provisions. Damage to any single cylinder typically resulted in an immediate and irreversible loss of coolant, which inexorably led to severe overheating and subsequent engine seizure within a matter of minutes. More significantly, the P-47's oil system had demonstrated astonishing resilience. While numerous oil lines had been entirely sundered and the oil tank exhibited multiple penetrations, the system possessed sufficient capacity and redundancy that, even with substantial leakage, enough lubricant would persist to maintain engine lubrication for the critical minutes necessary to reach friendly airspace. In stark contrast, German fighter aircraft carried smaller oil reservoirs, often positioned in highly vulnerable locations. A single 20 mm projectile strike to the oil system of a Bf-109 was tantamount to an immediate incapacitation, sealing the engine's fate. The examination of the fuel tanks arguably constituted the most impressive discovery of the entire assessment. The self-sealing tanks were not merely a simplistic rubber coating. They represented ingenious composite constructions comprising multiple sophisticated layers. The outermost layer consisted of conventional aluminum, primarily serving to maintain the tank's structural integrity and provide inherent strength. Beneath this, a layer of vulcanized rubber was present, followed by a layer of untreated rubber, and finally, the innermost layer designed to contain the fuel. When a bullet or a fragment of shrapnel passed through, the aviation fuel would interact with the untreated rubber layers, causing them to rapidly swell and distend, thereby physically occluding the aperture within seconds. While German engineers had previously encountered self-sealing tanks in British aircraft, the American implementation was demonstrably more resilient, possessing the capacity to seal wider breaches and withstand numerous penetrations. The rigorous test had inflicted approximately a dozen 20 mm holes across various fuel tanks, and every single one had either fully sealed or was actively in the process of sealing. Admittedly, fuel had initially leaked out, but the leakage had either completely ceased or decelerated to an inconsequential trickle. More profoundly, the tank's internal structure had successfully averted the type of explosive fuel vaporization that invariably led to catastrophic fires. The internal baffles and the specialized foam filling present in some tanks meant that even high explosive rounds could not generate a sufficient fuel mist to ignite. An Allied pilot might indeed sacrifice 20 or 30 gallons of fuel due to combat damage, but he would not forfeit his life to a devastating conflagration. The control system's damage told a narrative of comparable significance. Multiple control cables had been entirely sundered, the very kind of damage that, under normal circumstances, should have rendered the aircraft unmanageable in flight. However, the P-47 incorporated a system featuring dual, and occasionally even triple, redundant pathways for flight control. For instance, the ailerons boasted two separate cable systems, each routed through distinct sections of the wing structure. Similarly, both the elevator and rudder were equipped with primary and backup control mechanisms. Consequently, even with several cables severed, at least one functional control path consistently remained operational. The controls might become more rigid or diminished in responsiveness, necessitating greater physical exertion from the pilot, but they would nonetheless function. A battle-damaged P-47 might indeed prove challenging to pilot, but it would remain eminently flyable. Even the electrical system exhibited judiciously integrated redundancy. It featured multiple generators, several independent battery systems, and strategically placed circuit breakers specifically engineered to contain disruptions within compromised segments. In contrast, a Bf-109 suffering electrical damage would frequently experience a complete and instantaneous cessation of electrical supply. The P-47, however, could sustain the loss of half its electrical system and still maintain electrical provision to essential instrumentation and communication apparatus. The engineers assiduously recorded every detail, diligently taking precise measurements, capturing photographic evidence, and collecting material samples for further laboratory analysis. Their preliminary conclusion was both inescapable and profoundly chastening. The Americans had constructed an aircraft that was conceived and constructed from its foundational components with an inherent capacity for battle damage endurance. This outcome was not attributable to mere serendipity or intrinsically superior materials. Rather, it was the direct consequence of a methodical engineering doctrine that accorded paramount importance to the preservation of aircrew and the retrieval of the airframe, often at the expense of minimizing weight or maximizing raw performance. The Germans had primarily focused on designing fighters optimized for winning aerial dogfights. The Americans, conversely, had dedicated their efforts to building fighters engineered to bring their pilots home alive. The technical report, meticulously compiled by the Rechlin engineers, extended to scores of pages, yet its essential conclusions could be distilled into one stark, incriminating declaration. German fighter design philosophy had been patently misaligned with the exigencies of the contemporary conflict. While the document did not phrase it quite that bluntly, military bureaucrats rarely do, the underlying ramifications were unmistakably evident to discerning observers who were adept at reading between the lines. The P-47 represented a completely divergent approach to air combat, one that consciously embraced certain compromises in exchange for formidable benefits pertaining to aircrew persistence and extended operational capability. The comprehensive armor analysis unveiled a meticulous consideration of projectile trajectories and statistical likelihoods. American designers had not simply affixed metallic shielding haphazardly onto the airframe. Instead, they had diligently studied the most probable angles of enemy fire during typical combat engagements and had strategically placed protective plating accordingly. For instance, the seatback armor provided robust protection against the most prevalent attack vector from behind and slightly above. The windscreen armor offered safeguarding against head-on attacks and effectively deflected fragments resulting from engine hits. Furthermore, the armor's thickness itself was varied based on the assessed threat probability. Critical areas received quarter-inch plate, while less vulnerable sections were afforded lighter protection. Although German aircraft also incorporated armor, it was minimal, positioned rather as a supplementary addition than as a foundational, interwoven component of the design. The sophisticated self-sealing fuel tank technology particularly captivated the German chemical and engineering specialists. They meticulously disassembled exemplary segments and subjected the elastomeric compositions to rigorous scrutiny under laboratory conditions. The system functioned through a precise chemico-physical interaction between aviation fuel and untreated rubber. When fuel contacted the rubber layer, it induced a rapid and significant swelling. This rubber possessed the remarkable capacity to expand to several times its original volume, thereby forming an occluding stopper that hermetically sealed breaches up to approximately 12 mm in diameter. While larger perforations might not seal completely, they would still significantly restrict fuel flow. Although the Germans possessed similar technology, their execution proved to be substandard. Their self-sealing tanks frequently failed after enduring multiple hits, whereas the American tanks demonstrated the ability to sustain numerous penetrations and continue functioning effectively. The philosophy of redundancy pervaded every operational subsystem of the aircraft, and this was perhaps the most challenging principle for German aeronautical designers to fully internalize. From their perspective, redundancy inherently implied additional weight, increased complexity, higher manufacturing costs, and a greater maintenance burden. Within the German military-industrial system, already stretched thin by the demands of a multi-front war, such ostensible lack of efficiency appeared nearly profligate. However, the American calculation was fundamentally different. The United States possessed superfluous manufacturing prowess, plentiful natural resources, and a strategic doctrine that valued trained pilots as invaluable, non-substitutable resources. Constructing a heavier, more expensive fighter that reliably ensured the safe return of its pilots constituted a more prudent allocation of resources than building lighter, cheaper fighters that invariably led to higher pilot casualties. The report also incorporated exhaustive computations regarding operational efficacy in battle. A Bf-109 might indeed possess enhanced agility and a more favorable thrust-to-mass proportion, but if it carried a 30% probability of being destroyed by damage, that a P-47 would unequivocally survive, then the American aircraft consequently demonstrated greater overall utility. Pilot training consumed months and represented an expenditure significantly exceeding that of any single airframe. Experienced pilots became progressively more indispensable at an accelerating rate as they accumulated invaluable combat knowledge. The Americans clearly comprehended this calculus. The Germans, too, understood its logic, yet their industrial capacity simply lacked the requisite manufacturing wherewithal to implement the American paradigm. One particular section of the report addressed a subject that would have been nearly blasphemous to articulate within official Luftwaffe channels: the psychological state and morale of aircrews. The engineers observed that American pilots, fortified by the knowledge that their aircraft could withstand prodigious damage and nonetheless ensure their safe return, would likely prosecute offensives with greater audacity and withdraw from confrontations with diminished alacrity. Conversely, German pilots operating in fragile fighters would inevitably cultivate prudence, electing to terminate engagements prematurely and demonstrating a heightened propensity to avoid unfavorable encounters. This profound psychological factor exponentially augmented the P-47's tangible benefits. The aircraft was not merely mechanically superior in terms of survivability. It fostered a psychological ascendancy, transforming American airmen into more formidable adversaries. The P-47 Thunderbolt's robust construction quality, particularly its ability to withstand severe battle damage, consistently garnered significant attention from its more dangerous opponents. This formidable attribute stemmed from manufacturing processes that German factories, by 1943, were simply unable to emulate. The meticulous application of uniform and precise riveting, alongside welds of unwavering excellence, underscored an industrial prowess far exceeding that of their adversaries. Crucially, components across P-47 airframes were fully interchangeable, an unprecedented advantage that German maintenance crews, accustomed to the laborious process of hand-fitting parts and improvising repairs in the field, found almost unfathomable. This remarkable manufacturing excellence translated directly into a strategic benefit. Even severely battle-damaged aircraft could be expeditiously restored to operational status using readily available standardized parts. In stark contrast, German fighters frequently necessitated custom fabrication for repairs, a time-consuming endeavor that devoured precious hours and increasingly scarce highly specialized manpower, further exacerbating their logistical challenges. The subsequent Rechlin report ultimately concluded with a series of recommendations that were paradoxically sound yet utterly unfeasible for the Luftwaffe to implement. It proposed that the German Air Force integrate redundant control systems, significantly enhance its self-sealing tank technology, bolster armor protection, and fundamentally re-engineer its combat aircraft with survivability as a paramount design imperative instead of an afterthought. However, actualizing these proposed changes would necessitate a complete overhaul of manufacturing facilities, the redesign of aircraft fundamentally from scratch, and the substantial reallocation of vital assets away from immediate production needs. Regrettably for Germany, it lacked the temporal window, raw commodities, and comprehensive industrial might required to follow America's exemplary manufacturing paradigm. Consequently, the Germans could only meticulously record their observations and insights, holding on to the faint hope that a series of minor, incremental improvements might eventually diminish the disparity in aircraft resilience. Once finalized, the report was officially endorsed, securely categorized, and broadly disseminated to the relevant engineering departments, where it merged with a multitude of prior analyses documenting the disquieting reality that Germany was steadily losing the technological and industrial war. The profound consequences of the Rechlin findings reverberated through Luftwaffe tactical planning with the force of an aqueous seismic event. For months, fighter commanders on the Western Front had harbored apprehensions that their established combat strategies were diminishing in efficacy against the formidable American heavy fighters. Yet, mere suspicion and empirically documented proof were entirely different matters. Now, they possess concrete engineering data substantiating the anecdotal accounts of their airmen. Engaging P-47s with traditional methods was unequivocally a profligate expenditure of ordnance and, more critically, a needless sacrifice of human capital. The Luftwaffe imperatively required innovative combat strategies, and they needed them without delay. The initial tactical adjustment mandated was arguably the most mentally arduous for their seasoned pilots. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. German pilots were henceforth mandated to disengage from prolonged aerial confrontations with P-47s whenever feasible. This directive fundamentally contravened the foundational tenets of aggression and relentless offensive action that had been ingrained within fighter pilots through years of rigorous training, emphasizing the destruction of the adversary. However, the intelligence derived from the Rechlin analysis clearly demonstrated that a Bf-109 or Fw-190 pilot could expend their full complement of ordnance into a Thunderbolt without securing a decisive victory. Conversely, that very same Thunderbolt, despite sustaining injury, could effortlessly obliterate the German fighter with a solitary, precisely directed salvo from its potent .50 caliber guns. The underlying mathematics were unsparingly straightforward. Trading shots with P-47s constituted an untenable strategy. Instead, German tactical documents began highlighting particular offensive maneuvers specifically designed to optimize the probability of inflicting irreparable harm. Pilots were directed to target the cockpit solely, where feasible, this being the minute objective where a single, successful hit could ensure a decisive destruction, irrespective of the airframe's inherent resilience. This new approach was, however, more readily imagined than practically accomplished. The cockpit presented a diminutive target on a rapidly maneuvering aerial platform, and American pilots were expertly trained to continuously employ erratic and serpentine flight paths, thereby rendering accurate targeting almost unattainable. Nevertheless, this strategy was deemed superior to squandering valuable ordnance on wing and fuselage impacts, which the P-47 was demonstrably capable of withstanding. Another proposed strategy involved engaging in frontal assaults via head-on passes. This maneuver served a dual purpose. It afforded the German pilot an opportunity to strike both the pilot's compartment and the power plant concurrently, and it effectively nullified the P-47's inherent superiority in protective weaponry. The Thunderbolt's guns, all situated in its wings, achieved optimal convergence at a predetermined distance, typically around 300 yards. At closer ranges or further distances, the dispersal pattern of projectiles was diminished in density. A head-on pass transpired with such rapidity that both pilots had only an ephemeral instant to fire, and the Germans' fuselage-mounted heavy weaponry held a marginal benefit in that momentary alignment of vectors. Of course, such head-on attacks were awe-inspiringly perilous, mentally arduous, and demanded unwavering fortitude. Converging at an aggregate velocity of over 600 miles per hour, with both pilots careening headlong into one another, neither contender willing to yield ground initially, it was a profound demonstration of bravery no less than proficiency. Some commanders proposed the outright disregard of P-47s entirely, prioritizing instead the destruction of the bomber formations they escorted. This, after all, was the Luftwaffe's foremost objective, annihilating the American heavy bombers that were methodically dismantling German industrial capacity. If the P-47s were proving excessively challenging to neutralize effectively, then perhaps a more advantageous strategy was to tolerate their proximity, deploy numerical superiority to lure them from the bomber stream, and then strike the B-17s and B-24s while their escorts were misaligned. This approach yielded sporadic success, but American fighter tactics swiftly adapted to thwart this approach. P-47 units began flying in multi-tiered protective screens, with some fighters maintaining close proximity to the bomber stream, while others conducted roving interception sorties at varying altitudes, poised to engage any German fighters that appeared. The mental repercussions of the P-47's profound durability extended far beyond mere operational strategies. German pilot morale plummeted when they grasped the disheartening fact that even flawless execution, achieving an optimal offensive stance, delivering numerous impacts, witnessing their ordnance connect with the target, could still result in the American fighter departing, emitting plumes of vapor, yet remarkably operational. This engendered a pervasive feeling of hopelessness, a sense that the adversary possessed superior engineering capabilities that individual prowess and valor were powerless to surmount. This was especially disheartening for seasoned airmen who had forged their renown through precision gunnery and strategic acumen. They had dedicated considerable time to perfecting their craft, and now that mastery appeared inadequate in the face of American technological superiority, maintenance and logistics officers derived their distinct insights from the Rechlin report. If P-47s were recovering to their airfields despite severe structural compromise that would have rendered German combat aircraft irreparable, it implied that American maintenance crews were investing immense labor in restoring airframes rather than fabricating fresh units. This indicated a potential weakness in the American supply network. If the Luftwaffe could inflict damage upon more P-47s that American maintenance facilities could repair, they could substantially diminish the active fleet size without necessarily achieving outright aerial victories. This realization led to a nuanced alteration in mission planning. Sometimes, mission success was reinterpreted as merely incapacitating an aircraft for an extended period, rather than achieving its complete obliteration mid-flight. By early 1944, Luftwaffe commanders recognized they were contending with an opponent whose manufacturing ethos diverged profoundly from their own, and this divergence was evidencing itself in operational superiority that was impervious to purely tactical countermeasures. The P-47 Thunderbolt's performance under fire at Rechlin thus transcended the status of a mere curious addendum in Luftwaffe intelligence reports. It signified a pivotal moment in how military aviation addressed the core inquiry of aircraft design priorities. The ensuing decades would confirm that the insights gleaned from that bullet-perforated airframe shaped the evolution of combat aircraft on both sides of the nascent geopolitical adversaries of the subsequent Cold War. The design principle emphasizing aircraft resilience, rather than solely agile platforms, ascended to the status of established dogma, rather than a subject of dispute. American aircraft designers leveraged the P-47's exemplary operational history and advanced its principles further. The Republic F-84 Thunderjet, developed in the late 1940s, adopted the fundamental genetic blueprint of its predecessor, the Thunderbolt, robust in construction, swift in flight, and engineered to withstand severe damage. This design ethos permeated beyond interceptor roles, extending into attack aircraft, such as the A-10 Thunderbolt II. Introduced in the 1970s, and remarkably still flying today, the A-10 was essentially the P-47 concept pushed to its ultimate practical conclusion, incorporating duplicate control mechanisms, a fortified pilot's enclosure, autonomously sealing fuel reservoirs, power plants strategically placed for mutual protection from ground fire, and the astonishing capacity to return safely even after sustaining catastrophic structural damage to 50% of its airframe. That formidable aircraft owes its genesis to the fact that the P-47 definitively validated the efficacy of the underlying principle. Soviet aircraft designers meticulously analyzed intercepted German reconnaissance documents concerning coalition airframes, including the Rechlin revelations. Post-war Soviet fighters subsequently showed a growing prioritization of aircrew safeguarding and the duplication of critical systems. This design principle manifested in platforms such as the Su-25, the Soviet counterpart to the American A-10, which integrated numerous identical resilience characteristics. The geopolitical skirmishes of the Cold War era, in Korea, Vietnam, and Afghanistan, provided perpetual corroboration that airframes engineered to ensure aircrew return were well worth their inherent mass disadvantages. Even the Germans themselves assimilated the crucial insight, though they learned it at a juncture where it could no longer exert meaningful influence. Late-war designs like the Ta-152 showed heightened focus on pilot protection and the resilience of their fuel systems. The nascent jet aircraft programs, particularly the Me-262, integrated autonomously sealing fuel reservoirs and enhanced protective plating as integral components, instead of belated additions. But by the point these enhancements were deployed in active combat units, Germany was devoid of the necessary aviation fuel, proficient airmen, and manufacturing prowess to affect any tangible change. The Luftwaffe, which had once spearheaded the development of contemporary aerial warfare strategies, discovered itself decisively outmatched by opponents who had excelled in both strategic methodologies and manufacturing output. The profound human toll inextricably linked to critical engineering choices became strikingly evident when analyzing the divergent pilot casualty statistics. While American fighter pilot fatalities in the European theater were by no means negligible, they remained markedly lower than those experienced by their German adversaries, particularly during the conflict's waning years. This notable discrepancy stemmed partly from a numerical advantage and superior training, yet a substantial portion was attributable to the sheer inherent survivability of their aircraft. American aviators frequently emerged from crashes and sustained battle damage that would have unequivocally proven fatal for their German counterparts. A prime example was the P-47, which could endure numerous perforations from enemy fire and still successfully complete its journey across the treacherous English Channel. In stark contrast, a Messerschmitt Bf 109 suffering comparable damage would invariably compel its pilot to eject over hostile territory, a scenario that, at best, resulted in capture and imprisonment. This pivotal legacy of survivability extends well beyond its initial military applications, profoundly shaping subsequent technological advancements. Modern commercial aviation's almost zealous commitment to redundancy, manifested in the incorporation of multiple fail-safe systems for every indispensable function, finds its foundational philosophical origins in the very same engineering ethos that gave birth to the resilient P-47. The iconic Boeing 747's quartet of engines, the intricate triple redundant hydraulic systems ubiquitous in contemporary airliners, and the sophisticated fire suppression mechanisms are all direct reflections of the enduring principle that ensuring the safe return of human lives unequivocally justifies additional weight, increased complexity, and elevated manufacturing costs. The physical P-47 airframe subjected to rigorous testing at land almost certainly did not endure the entirety of the war. Historical records strongly indicate that the majority of captured aircraft housed at the facility were either obliterated during relentless Allied bombing campaigns or were systematically destroyed by retreating German forces, meticulously preventing their potential recapture. Nevertheless, the aircraft's profound influence persisted, indelibly etched into the collective consciousness of every engineer and pilot who meticulously scrutinized those pivotal test results. They had unequivocally witnessed irrefutable proof that an aircraft could be meticulously engineered to withstand a degree of punishment previously deemed utterly unsurvivable. This singular, groundbreaking revelation irrevocably transformed the prevailing conventional wisdom regarding the design and construction of future fighter aircraft. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. In the contemporary era, the survivability of military aircraft stands as a paramount design consideration, integrated from the earliest conceptual phases rather than being relegated to a mere afterthought. While innovations such as stealth technology, sophisticated electronic countermeasures, and advanced composite materials have undeniably revolutionized the specific methodologies employed, the fundamental underlying philosophy remains steadfast. The most effective aircraft is ultimately the one that consistently delivers its pilot safely back to base. The legendary P-47 Thunderbolt, stoically positioned within that German test range, absorbing volley after volley of 20mm cannon fire and steadfastly defying destruction, validated this crucial principle in the most unequivocal and direct manner imaginable. German engineers had initially embarked on their investigation with the specific objective of comprehending precisely why these American fighters continued to survive such brutal encounters. They not only received their answer but meticulously documented it, thereby inadvertently helping to forge the foundational blueprint for every subsequent combat aircraft. The test, initially conceived to unmask inherent weaknesses, instead dramatically unveiled a revolutionary paradigm shift in aviation design philosophy, a shift destined to outlast the tumultuous war, transcend the protracted Cold War, and continue to profoundly influence aircraft development well into the 21st century.